Alright, good morning. This is the last lecture of the course and we will look at the bipolar junction transistor. This is just an overview of the existence of this kind of device. How is it different in a sense from the MOSFET? We will only look at the circuit characteristics. We won't look at the physics of how the device operates, that you will learn in a course next semester on solid state devices. I just want to give you enough information for you to appreciate that they are very similar, but there are some small differences which you have to keep in mind. Okay. So, let us see if we can go over this quickly. Alright. So, basically so far we have been discussing the MOSFET, and this for example is your NMOS device. You had the gate, you had the drain and you had the source, correct? Similar kind of device, another 3 terminal device is the bipolar junction transistor. It is not drawn with that line. Okay. Many of you have already used the bipolar junction transistor. So, corresponding to the gate, the terminal is called the base. Corresponding to the drain, it is called the collector. Corresponding to the source, it is called the emitter. Okay. So, this is your NMOS device and this is the NPN BJT. Okay. So, the NPN refers to the fact that in its construction you actually have an N region, a P region and another N region, where this is the collector, that is the base and this is the emitter. Okay. You will discuss, you will understand why this kind of structure gives you the kind of performance and all of that later. Okay. So, what we are interested in are the terminal characteristics. So, what are the currents and voltages that you might be interested in here? What were you interested in here? What was the input voltage that controlled everything? It was VGS, right? VGS was what set up the current in the transistor, and the current that was flowing here was the drain current ID. Here, what do you think will be the voltage? Plus minus VBE, that is the voltage which sets up the current, and the current that is flowing through the collector is called the IC. Interesting thing for the MOSFET was that the gate current IG was 0, right? For the bipolar transistor, it is not 0. You actually have a gate current called IB. Okay. So, then can you tell me, if I mark IE, which is the emitter current, in this way, can you right, you just apply Kirchhoff's law. So, you will have IE is equal to the collector current plus the base current. Okay. And what are the characteristics of this device? So, we should draw the characteristics, but before that you possibly have already seen this somewhere, that the collector current IC is, or rather the base current IB, right, base current IB is what? No, yeah. So, it is IC divided by beta, and beta for a typical transistor is about 100. Okay. It will vary, maybe 50, maybe 100, maybe today 50, tomorrow 100. If you take it near the generator where it is very hot, it may become something else. Okay. It varies, but it is of this order. Alright. So, how do you think the terminal characteristics of this device will look? Let us look at the output characteristics for now. So, what do you have to plot here? VBE, correct. Think again, output characteristics. So, what do you plot here? VCE and IC, and you might have seen this. Okay. Let me draw this and then I will explain what are the key differences between this and the MOSFET. Okay. There are innumerable number of devices which give you the kind of saturation characteristics that are required for an amplifier. The MOSFET and the bipolar junction transistor are but 2 of them. Okay. You can have things like the high electron mobility transistor, which works at very high frequencies. You have hot electron transistors. You have a whole family of these devices. But for normal, the most popular device today is the MOS device. all of your digital electronics is enabled by MOS, and because of that many circuit designers want to make analog circuits also with MOS, so that you can have a single silicon wafer on which you can have both analog and digital circuits, which is what your phone is, for example, right? You need to have amplifier blocks and filters and all of that, those are all analog. Then you might have some digital logic, and then again you want to drive a speaker and all of that, it's again all analog. So in order to facilitate both analog and digital circuits living on the same wafer, people prefer to make everything in MOS these days. However, the bipolar transistors are still popular for certain applications. For example, we did not talk about the power amplifier stage, right, when we looked at the two-stage op amp. Many of the power amplifiers that go into your cell phones are actually made in bipolar. So there is a technology called the BiCMOS technology, which is a process flow which allows you to make both bipolar transistors and MOS transistors on the same wafer at the same time. Okay, it's an intelligent workflow. You'll see that later. The speaker who came last semester, for example, and spoke about inductors and all of that, if you remember those who attended there, he mentioned that the last stage power amplifier design is actually very, very key today, and that in fact limits the choice of companies whom a phone manufacturer can approach. There are a large number of companies that give you the technology for fabricating all of these MOS transistors, and also the circuit libraries that you can use then to simulate. But many of them don't have very good power amplifiers, and hence in the long run people don't prefer using those technologies. Okay, so the bipolar transistors are important, and when you do a discrete kind of design, you will see that bipolar transistors are still very, very popular, right? Also for power amplifiers and things like that, the bipolar is also still quite popular. Now, how do you think this characteristic should look in essence? You should have something like that, and then saturates, right? And then, right? So if this is VBE1 and this is VBE2, with VBE2 being greater than VBE1. Okay, but note that there is an important difference between the saturation characteristics of this behavior of this device and the MOSFET. First, there is if you look at this kind of this transition region, it is not a parabola anymore, it is a vertical line, so it's easier, okay, for design and everything. So it's a constant voltage. The second thing, which is a little more painful for people to understand, is that the terminology has changed. So in a BJT, the saturation region is not this region where the curve is flat. The saturation region is this region. Okay, the terminology is poor, it's not consistent, and the reason, so in the MOS literature, saturation refers to the fact that the current voltage characteristics saturate. Okay, however, in this, the saturation actually refers to a physical phenomenon that is happening in the device, and that phenomenon saturates. Okay, so that's why there is a difference in terminology. So keep this in mind. So you want your MOS transistor to work in saturation, you want your bipolar transistor to work in this region where things are pretty much flat, and this region is called the active region. It is in the active region that you can get gain, right? For gain, you need this thing to be reasonably flat. All right. So for your bipolar transistor, you have to work in the active region. For the MOS transistor, you work in the saturation region. Okay, keep this in mind. Poor terminology, but that's the way it is. Okay, whoever invents something has the freedom to call it whatever they want, and then if enough number of people start calling it that, even if the name was bad, it still sticks, right? Like the nicknames you give people. Anyway, so this particular thing, this transition, right, is called VCE SAT. All right, and this refers to the minimum value of collector emitter voltage that you require in order that the device goes into the active region, and this can vary from anywhere from 0.2 to 0.7 volts depending on the device and all of that. Okay, typically you know, you can assume any voltage, but for today's discussion let me just assume 0.65 volts. Okay. You look up the transistor data sheet and then you will find this value and then you can proceed. Okay. And also these characteristics are not necessarily perfectly flat, as you saw in the MOSFET. Again, the physics of why it is not flat is different, but you will see that it is not flat. And so the characteristic will not look perfectly flat, you will have a certain slope like this, right? You will have a slope like that. And so we can write out now the characteristics. We are pretty much interested only in the characteristics in the active region for today's discussion. So in the active region, can someone tell me what the characteristics will look like? So you have IC is essentially some saturation current Is into e power VBE by VT minus 1, and this IB is IC by beta. Okay, yes, and I forgot to add that, which Prasanna was hinting at. I have to add something here to account for this non-flat region, and that is written as 1 plus VCE. So in the MOS literature, what did you have? You had a lambda. But in the BJT literature, they don't give a lambda, they write it as VCE by something called VA, right? And this VA is called the early voltage. It has nothing to do with the fact that somebody came early and somebody came late. It's after the name of a person called Early. Okay, he was an engineer at IBM, and there's a very interesting story about how he discovered the fact that there is this kind of relationship. In fact, you can prove it that if you, I have not drawn it nicely, but if you extended all of these lines back into the second quadrant, you will see that all of these lines actually intersect, and they will intersect at the value given by this VA or minus VA. Okay. So it's just a terminology. What is this VT? It is not the threshold voltage, it is the thermal voltage. Which is around 25 millivolt at 300 Kelvin. No. Well, it might again, but people don't worry too much about that. It's depend on the material. I think it will be dependent on temperature also. I'll have to go back and check the exact dependence. There might be a small dependence. Everything usually is dependent on temperature. So because the material concentration, everything will change with the temperature, right? You can ask Anuja, she has been preparing for some exam on BJTs. Does it depend on temperature? Does it go up or come down, saturation, VCE sat with temperature? I'll have to go check, I have forgotten. Okay, anyway. Okay. So there is a dependence. Huh? No, obviously not. It is, okay, sorry, I have written it wrong. This is exponential of that minus 1. Okay, all right. Doing this, I just remembered that a few days ago we made a goof up in class and none of you caught me. So let me just correct that so that at least it goes, when you are preparing for the exam, it's all correct, right? When we did this plot, what was this plot? We had first the system without compensation, had 40 dB per decade roll off, then you put a dominant pole and then you got this thing, right? And this is the phase plot corresponding to what? This is no compensation, right? And the moment you put this thing, it should change, right? We were trying to plot it on the same thing, and that's why it did not look correct. So you actually should plot another. So if you take this guy, how will its phase plot look? At this point, it should go to minus 45. At all of this region, it should go to minus 90, and then here it should come to 135, and then you are down here. Is that right? Okay. So that phase plot for this compensated guy should actually look something like that. I'm sure all of you can figure this out, okay. And that's why if you now look at the loop gain or the unity loop gain and look at the phase margin, we have already calculated how much should this approximately be, around 76 degrees, because we in fact did the compensation, if I remember right, for unity loop gain, right, sorry, for zeta equal to 1. That's how we started, no, we wanted zeta equal to 1 and we did this, right. So this is the guy with compensation. Okay, I remember this somehow, I don't know why. Anyway, let's proceed. Okay, so now we have this, and can you now work out what's the next thing that we need to work out for this particular device? These are the large signal characteristics. What should we now work out? The small signal characteristics, right, in the incremental picture. Can you work out the 2-port Y parameter network for this? Okay, forget VCE by VA for some time, we can add it later. Okay, without the VCE by VA, can you work it out? Your transistor itself was this. I think we did this in the previous semester for a course, for an exam, right? I gave this in an exam, right? So this is plus minus VBE, this is IB, this is IC, plus minus VCE, and IE you don't need. Okay, this for the 2-port network you don't need that, right? So 2-port parameters, this will be V1, this will be V2, that will be I2, and that would be I1. Okay, I have just drawn everything as capital letters, but I am not going to rewrite everything. All of these should be incremental quantities. Okay, so write the answer in terms of incremental quantities. I have written everything with capital, that is not correct. All right. So what should the Y parameter network have? What would be the what would be on the left hand side, and what would be on the right hand side? You will have the Y matrix. On the right hand side you will have what? So this is V1, right? I1 or V1? I. Okay. So this is I1. So let me call that as I small b, and then I small c, and here this will be V BE, and this is V CE. Okay. So some of you people in your answer scripts, your handwriting does not allow me to distinguish between small and large. So if you feel that you cannot use this small letter, capital letter correctly, start using Greek letters or something and just write a note that all my incremental quantities have Greek subscripts or something like that, right? I can't distinguish whether you are writing a small v or a capital V. It becomes very difficult, right? In fact, I have made a note on that. So if you come back and explain to me as to what that is, I might consider, but I couldn't figure out what it was. All right. Okay, be careful when you write. Anyway, nowadays everyone will type things out, so it's okay. Anyway, all right. So you will have Y11, Y12, Y21 and Y22. Can you quickly tell me what these parameters are? What is Y11? Right. So it will be dou I B by dou V BE. So what is that going to be? Quickly. Right. Your IB is nothing but okay. Now again, is this right? This is not right, right? Okay, let me clean all this up and write it correctly, because people will get confused. Sorry, let's not skip steps, bad for health. Okay, so this is VBE, right, incremental. This is VCE, incremental current IC, incremental current IB. Similarly, this is incremental V1, incremental V2, incremental I2, incremental I1. All right. But when you are calculating Y11, you should not take the incremental thing. You should take this as dou what? So it should be dou IB by dou VB. Correct? Because that is the operating point. So what would this be? This would be 1 by beta times dou IC by dou VBE, and what is this? 1 by beta into, so forget about this minus 1 also, right? Forget about that minus 1, forget about that for now. So just you have this. So what will that give you? IS by VT into exponential of VB by VT, which is essentially equal to IC by VT with a 1 by beta. Is that right? That's with the exponent. All right. Then what about the other parameters? Can you tell me what y12 is? This should be dou IB by dou VCE. Okay. Now I told you to not take it, but if you did take it, what will it be? Can you see that it will be IC by VA, right? It will be IC by VA roughly if you took it into account. Anyway, you can go and check that out. What is y21? IC by dou VCE, and that is nothing but this. We have already not VCE, VBE. That is your IC by VT, and that is identical to your GM, right? So this quantity is nothing but what? This is GM by beta. All right. And finally, what is y22? Dou IC divided by dou VCE, and what is that? Okay. Now, sorry. Let's take this as 0. Okay, IB is very small, so when you are doing IB, you can forget about early voltage and all of that. So that's small, so make that 0, and here you include the early voltage. So this becomes IC by VA. Okay. That's why, anyway. All right. Okay. So what is the incremental circuit going to look like now? You have done this. I should have a, so because this y12 is 0, right? You won't have any voltage source here. You will have just this. What is the value of this resistor? It will be 1 by y11, right? So it will be beta by GM, and then on the other side you should have a current source. What is this going to be? GM times VBE, and then I have an output resistance R0, which is IC by VA. All right. So this is your emitter, this is base, this is again emitter, that is collector. Yeah, VA by IC. All right. So compare this with the MOS. What is essentially different? What's the main difference between the MOS and this? You have this resistor. Okay. This is the main difference. Between the MOSFET and BJT. All right. Okay. So this is the incremental picture. I just forgot something about the large signal picture, so let's just go back and I will introduce another slide here. So here you plotted IC versus VC and you got this kind of characteristic. All right. Now look at this. Look again at this thing here. Okay. Maybe we take this whole thing. Right. So can you tell me if I were to just look at how IC in this active region, how does IC depend on VBE? So I want to just plot for fun. Okay. Let me say that this is IC and this is VBE. Okay. How do you think this will look? Just plot, only look at this characteristic, right? It will be exponent, but because I have flipped the axis, it will look something like this. Is that right? All of you have plotted this. This is basically the diode characteristic, but instead of looking at it with VBE on the horizontal axis and IC on the vertical axis, I am just looking at it with VBE on the vertical axis and IC on the horizontal axis. And all of you remember that when we did this, right, for the diode in the first few classes, we said that the voltage across the diode itself does not change significantly. You can assume 0.65, 0.7 and proceed, right. So, that is the same thing people do even for this, and that is why the analysis of BJT circuits is actually much simpler, because for most practical values of current, your VBE does not really vary much, right. So, what people do is to just take some nominal value somewhere in the middle, right, and say that I am just going to work with that. And what we will do for today's discussion is to assume that this nominal value of this thing, so let me call that VBE nominal, we will assume that also to be 0.65 volts. Okay. So, many of the things are much simpler with the BJT, all right. So, this you can keep in mind. And is there anything else? Yes, there is one other thing that we should keep in mind, that if you look at this kind of circuit, again because of the fact that VBE is actually, or rather the current is exponentially dependent on VBE. If you were to make this kind of plot, you will have VBE 1 as 0.65, VBE 2 will be 0.66, things like that, right, because even for very small changes in your VBE, you will see significant change in your current. So, what people do is to not plot it like this, but rather think of a biasing arrangement, something like this, right. I have my BJT like this. Let me call this as VCC, that is 0. Okay. I want to measure my collector current, so I put an ammeter here. That is an ammeter. I have to change my base voltage, so I can cook up an arrangement something like this, right. I can have some variable RB here, and let me say I put something else here, let me call that as some RA, okay, or maybe because we will in the subsequent discussion we will have RA and RB flipped, so I will flip it now itself. So, I will have RA here and RB like this, right. So, if I change my RA, I can change VBE, right, and what will happen? That will also change the current flowing here, right. So, basically, can you go through this loop and tell me something? Go like this, like that and like that. What can you tell me? In fact, for this particular thing, you do not even need this RB here. Yeah, we do not need this RB. Okay. This kind of thing, based on this analysis we did here, can you approximately at least write this VCC minus IB times RA, right, minus VBE. Once the device is on, the VBE nominal is about 0.65, is 0, right. So, this roughly relates your, so you can get IB as VCC minus 0.65 by RB or RA, right, the way we have drawn it, it is RA. That will give you your base current, and once you know the base current, you can find out what my VBE is, right, the actual value of VBE, by saying that this is VCC minus this base current into IB. Okay. Anyway, there is a little bit of complication there, we do not need to worry about that. Essentially, people do not plot it in terms of VBE, but rather use IB as the knob. So, you change IB and you look at the characteristics. So, most bipolar junction transistor characteristics, if you see in your data sheet and so forth, you will not see VBE there, right. You will see a characteristic like that, similar to what we have drawn, but only thing is that this will be they will say this is IBE1, this is IBE2, this guy is VCE, and this is IC. Okay. So, the characteristic is the same, is just that you will use base current to label the curves. So, typically you may see something like this is 10 microamps, then 20 microamps, then so forth, right. At least this will make sense rather than having VB equal to 0.65, 0.66, 0.65, 662, things like that. Okay. All right. Now, we know enough of this now to look at just the common source, the equivalent of the common source amplifier, and that with that I guess you will have an idea of how to make BJT circuits. Okay. So, corresponding to the common source amplifier, you have the common emitter amplifier. So, what is the first thing that you need to do when you make a circuit with for an amplifier? You have to bias it. Very good. So, we will first look at biasing. Okay. There are many kinds of biasing that you can do, but the important thing to remember is the following. If I have a BJT like this, right, forget about what is there in the collector arm for now. Let me say that is VCC, okay, and something here. For a MOS, we started off our initial biasing by saying that we will just have an RA and RB and we will bias it with a voltage, which means you are going to control this VB voltage, right. That was how we started the MOS biasing. But if you remember, for the just the discussion we had little while ago, current is exponentially dependent on base emitter voltage, right. For the MOS, it was only quadratically dependent. Here it is no, sorry, not quadratic. Yeah, it was quadratic. It was VGS minus VT whole squared. Here it is exponent. So, the rule which is quite evident is never bias using a voltage for VB. Let's don't use a voltage source. Don't do this kind of. Don't do this. Why should you not do this? Yes, the variability will be very, very high and your circuit will never work. Okay. So, what is the alternative? You use one of the feedback wait, you will see that we'll finish that. We'll come there. Okay. Use one of the feedback biasing arrangements. Okay. So, what are the feedback biasing arrangements? You can use a current mirror, you can use source feedback, you can use drain feedback. Okay. So, right now I don't have time to discuss which of the feedback arrangements is the best, but the most popular one for this is actually the equivalent of source feedback, right, and hence it will be called what? Emitter feedback. So, can you quickly tell me how this may look? I have my BJT here. What should I put here? I should put a current source. Very good. And then here I can have some kind of load here for fun, does not really matter, alright, and that is VCC. And what about the base voltage? What did we do for the MOS in order to get the gate voltage? We had an RA-RB. Alright. So, this is the common feedback arrangement that is used for BJT circuits. What is it that we have to keep in mind here? The important thing we have to keep in mind is that this voltage here is not just RB divided by RA plus RB into VCC. If I look at this VB, why? Because I have a base current also flowing here, correct. So, what typically people do is that you try and make the current that is flowing in this vertical direction very high. If you make the current in this vertical direction very high compared to IB, right, then you can forget about the IB. So in the MOS transistor world, there was no restriction on the actual values of RA and RB. The only thing that you had to keep in mind was the ratio of RA and RB. Here, in order to ensure that this bias voltage does not shift too much depending on the base current, you try and ensure that this vertical current is much higher than IB. Okay, so ensure that, what is this vertical current? Very crudely, VCC divided by RA plus RB. Okay, this will be exact if there was no IB. If IB was there, this is not going to be exact, but try and make this much greater than IB. Again, the way you are going to design this is the following. You want a certain GM, that means you want a certain IC to flow, right? This is your IREF. So say I want 1 milliamp of current to flow, correct? In order that I have a decent GM. What will my GM be if IC is 1 milliamp? If IC is equal to 1 milliamp, GM is IC by Vt, which would be how much? 1 by 25, right, which is equal to 40 millisiemens, correct? So this is independent of VCE, which is different again from your MOS world, but anyway, alright. So you ensure that this current is much larger than this current. And then what more can you do? I have this IC flowing here. This is nothing but IE, right? IREF is identical to the emitter current. How can you relate these three things now? Your IE is equal to IREF is equal to IB plus IC, and this is nothing but IC into 1 by beta plus 1, correct, because IB is IC by beta, correct. So if this is equal to beta plus 1 by beta times IC, if beta is large enough, this is approximately equal to IC for large beta. Okay, say if beta is 100, it will be 101 by 100, it's okay, it's roughly the same. Okay, so if I want 1 milliamp say of current to flow here, right, I can choose a current source also of value 1 milliamp. If my beta is 100, okay, if beta is 100, what will this be? 1 milliamp divided by 100, that will be 10 microamps, right? Is that right? It's 10 microamps. So say this VCC were 10 volts. So you ensure that VCC divided by RA plus RB is much greater than 10 microamps. That will give you your VB, right? And then you can bias this circuit. Very straightforward. So biasing this is extremely straightforward. Okay, with this bias, how will you make your amplifier? So we have made the bias. Now to make the amplifier itself, what should you do? I have to just include, I have to couple the load, I have to couple the source for this, right? So I have my biasing arrangement like this. I have a current source here like this, right? And I have to couple my input. So how do I couple my input? I put a capacitor here, some resistor, that is my V in, that is RS, okay? And then where should I take my output? This is VCC. I take my output here. This is my V out. And do I have to do anything else? You remember, this is like your source feedback. So this, in the incremental circuit, this current source will be open, right? So you need to put a capacitor here so that this works. Okay. Now can you quickly draw the incremental circuit for this? How will it look? Let me call this as RA, let me call this as RB. How will the incremental circuit look? We have done this many times, right? So you will have your RS, you will have VI, the capacitor will be a short, what about this RA and RB? You will have that RA and RB in parallel, right? I will have RA, RB, and then what else will you have that we have forgotten? Okay, let's put what we know already and then come back. This will be GM times VBE. I will forget about the output resistance of the BJT itself. They will just have this RL here. Okay, have I forgotten something? I have forgotten my what resistor? Which resistor have I forgotten? Yes, right. So I have forgotten this resistor, this beta by GM resistor, which has to exist between B and E. So where will that come? So if you name the terminals, right, this is my base, this is my collector, this is emitter. So I need to have another resistor here, which is beta by GM. All right. So now can you write out what is available for you? So what is VBE in terms of VEI? Very straightforward. What will it be? What is VBE in terms of VI? It's just the resistance divider, right? So it will be this guy, beta by GM parallel RA parallel RB divided by this same quantity plus RS. Okay, this dot is that quantity, and you want to make this approximately equal to VI. So you choose your RA and RB correctly. Remember that for the MOS the absolute values of RA and RB were not important, but here it is important because you have to ensure that this IB is small compared to this. So you have to keep that in mind. So you don't have as much degree of freedom, but you can still work something out. So it won't be valid for all values of RS, but if you know the value of the source resistance or a range of the source resistance, you can find things out. All right. And then what would V out be? V out will be minus GM RL times VBE, and if VBE is approximately VI, so this will be your gain. Correct? So if I assume the values that I was working with earlier, if I took this was, what was the value of this? 40 millisiemens, and say I assume RL was 1K, I will have a gain of minus 40. Say IC were equal to 1 milliamp and RL was 1K. Okay. All right. Now we'll just finish with one small thing. You remember that if you looked at this kind of bias circuit, when we discussed the MOS, the source feedback biasing, right? We discussed something about this current source. What did we say? We can replace this current source by a, yes. And what should that be? It should be a large value, we said, right? Why? So go back and look at why we discussed that, why should that be large. Okay, let's not spend time on that now. Go back to the notes on the source biasing arrangement and see why we had kept that as very large. Okay, now so if I replace it with a resistor, what will happen? I'll have this biasing arrangement like this. Okay, let me keep this. So this I'm going to remove, and I'm going to put in some value of resistor here and call this some RE, and the current that is flowing here is again going to be 1 milliamp, and you can work out what RE is. How will you calculate what RE is? How will you calculate RE? So the design step will be something like this. I want my IC is approximately IE approximately equal to 1 milliamp, okay, which means your IB is approximately equal to 10 microamps. Now you want this VB, right, divided by RA plus RB to be much greater than IB. So much greater than greater, you can assume 10 times. So this is approximately equal to 0.1 what? 0.1 milliamp, right? You can assume 0.1 milliamp. Okay. Then you also need to do something about your beta by GM parallel RA parallel RB must be greater than RS, right? You know what your beta is, you know what your GM is. So from these two equations, you can roughly work out what RA RB are. So if you have RA and RB, you will get what VB is, because VB is essentially, once you ensure that this current, this vertical current is much more than this IB, your VB is nothing but RB by RA plus RB times VCC. Okay, so you know what your VB is. If you have VB, I want to find out what RE is. How will you calculate what RE is? Just go through this loop. So you will have VB minus, you know VB already, right? I have told you that VB is around 0.65 volts. So 0.65 minus IE RE is 0, implies you can work out what is RE. Okay. So this is a very common biasing arrangement for the BJT, right? It is derived from the emitter feedback circuit, but this particular circuit has a name, and you will see this very popularly used. This is called the 4 resistor bias circuit. Alright. So this is what Prasanna was asking, right? So if you look in many of the circuits that your people have worked out, you will see that you just have 4 resistors. You don't have any current source there. But in effect, what it is doing is to mimic the behavior of the current source. Alright. So what we have done today is to basically introduce the bipolar transistor, right? Look at its large signal characteristics, get a feel for what the small signal equivalent circuit should be. Understand that the main difference between this and the MOS transistor is the existence of this input resistance, which means that your base current is not 0. So you have to keep that into account when you are designing circuits. Then we looked at one typical biasing arrangement, which derives from the source feedback arrangement, or equivalently the emitter feedback arrangement. We looked at an amplifier, right, including that kind of arrangement. And then I discussed that more practically we replace that current source with a resistor, and this kind of biasing arrangement is called the 4 resistor biasing circuit. Okay. I just do one other thing for you to just think about, and we can close with that. We said that we can think, for example, about a current mirror, right? So how will the current mirror look? I can have a situation something like this, right? I have some current flowing here through a current source. I have one bipolar transistor like this, and then I connect these two together, and then if I call this as some I naught, right, I call this as VCC. I want to find out what is the current through this. Assume that these two transistors are identical. So what do you think will flow here? Can you quickly tell me? Just for fun. Okay, it will be close to I0, right? But you have to account for the base currents. So this base current, say, is going to be IB. Both transistors are roughly the same. So you are going to have this current also as IB. So what is this current flowing here? 2IB. If 2IB is flowing here, what is the actual collector current? I naught minus 2IB. Correct? And if this is the collector current, what is the emitter current? I naught minus 2IB divided by beta. Sorry. So it's going to be I naught minus IB, right? And so the current that's flowing here is going to be I1 would be what? So this current will flow here, I naught minus IB. So what is the current flowing here? I naught minus 2IB. Okay. And can you work out what IB is in terms of I naught, in terms of beta? This is very straightforward, right? Because if I take this collector current, right, my collector current is I naught minus 2IB, and we know that IC by beta is IB. So you put so IC is nothing but I naught minus 2 times IC by beta. So what is IC? Is going to be I naught into beta what? This will be that it will be beta plus 2 by beta, or the other way around? Okay, let's just work it out. Okay, this will be IC into 1 plus 2 by beta is equal to I naught. So I was correct. Okay, so if you have I naught flowing here, the current that is flowing here will be how much? It will be this I naught into beta by beta plus 2. Okay, so there will be a small mismatch between the current that you are the reference current and the other current. So you have to keep this into account when you do things, and that is why in many op-amp circuits you will actually have a circuit, you will have, instead of in the input stage, the differential amplifier, instead of having a single BJT, will actually have a connection like this. We have seen this already. What happens now? You will have something like this. Yeah, right. So this is your Darlington pair. We saw this, right, somewhere earlier in your ULN had these Darlington pairs, right? So if this guy had a beta and this had a beta, the net result is going to be beta squared, roughly. Okay. So if you have this, so if you replace all of these things by this guy, right, your beta will go up. So the matching between things will improve. So just the take home from this is most differential amplifiers have Darlington inputs. Okay, all right. So that's pretty much what I want to do about bipolar transistors. Tomorrow we will